Welcome back, everyone. So for the first talk of the afternoon session, it's a pleasure to introduce Pekka Pankka from Helsinki. We'll be talking about the Rham algebras of closed quasi-regularly elliptic manifolds or Euclidean.
Thank you, Rand. I would like to thank the organizers. This is my first time visiting Fields Institute. It has been a great pleasure to be here, and I'm looking very much forward this week. I would like to comment the title. As a kind of good math title, it is very accurate, but totally impossible to understand. But there are two reasons why I wanted to talk about this thing. The one is that I think so that those who are about my age, they know that they have their kind of favorite problems that they have been thinking about since graduate school. And as Rand said, that sometimes it can take some time to finish the project. And so what I'm going to talk about today is something that kind of inspired me in my graduate studies, and we finally made progress in it. And the second, okay, so that what was needed that I am not a graduate student, but then you have a graduate student. That was the important thing, I think, in this project. And then the second reason I wanted to talk about this. So the actual topic, the actual result doesn't have dynamics in it, but actually the ideas that how do you reach the formulations and how do you find the result. Actually, there's a dynamical component there, so that there's analogous results in dynamics, and I like to kind of little bit mention also them, so that there is a little bit of these two topics in this talk. Okay, but let me start from something kind of quite classical. So that this whole thing kind of comes from complex analysis of one variable, so from holomorphic functions originally. So that if you have the classical result is that if you have an entire holomorphic function to a closed Riemann surface, then the surface is either a sphere or a torus. And so that if you think about that, how to prove that, so that the nice way to do it is that you take the surface and you take the uniformizing map to the universal cover. You notice that if the universal cover is a disk, then your lifted mapping dies, be a constant, and that's not a possible case, and so that you are left with the sphere. So, but the direction where I like to kind of push this is that if you take this two-dimensional result, then it actually doesn't really matter that you really have a holomorphic map. It doesn't really matter that the map is conformal. If you allow a little bit of distortion for your mapping, the result doesn't still the result still doesn't change. Meaning that if you allow a little bit of distortion, then the possible targets are still sphere and topological. So that the mappings that kind of what I'm kind of trying to here a little bit illustrate. Let me draw this map kind of one more time, and then little bit indicate what I mean by the distortion. So the mapping is very similar to what Daniel was doing earlier today. So you take a checkboard, and now you notice that you can actually do the checkboard in any dimension. You just, instead of seeing squares, you see cubes of the right dimension. And then kind of what you do is that you, okay, if I have 4 colors, so you mark the vertices like this, and then you should extend periodically, but let me just draw one set of vertices. You have a sphere here, let's say. You have the S2 in this picture. So here you have C, which is R2, and you have the sphere, and then you put the, so, okay, so now you notice that I never really care about orientation, so, but let me try to be still a little bit systematic with my colors. The idea is that you have the marked vertices here on the equator. You map the vertices to vertices, you map the edges to edges, and then you decide that one of the hemispheres is black, one of the hemispheres is white, and then you map the square to the hemisphere with a biellipsis mapping which coincides with the boundary data. And then when you go across, you go across, and you construct the mapping in this way. So that of course you can do this in a kind of even in a holomorphic case and so on. But kind of that what I wanted to a little bit mention here is that the mapping that the maps that I typically consider, they are not really smooth. There is no derivative at these corner points where the map fails to be locally injective. It is biellipsis here inside, and there are these type of phenomena. This is kind of the category of maps I'm looking. And if you think about what are the kind of where these type of mappings arise. So if you, for example, you have a triangulated manifold, and you can put the black-white coloring to the triangulation, then you can map it to a sphere with this type of technique. So this is kind of the context where you can think that these mappings arise. Okay, so now let's see what are the formal definitions. So now we go again back to the earlier talks a little bit. So that the class of mappings, what I'm considering, is called quasiregular maps. And the idea of the distortion is described by this inequality. So there is always you put some analytic regularity in order things to work, but I don't mention it anymore after this. So that there's analytic regularity. The more important thing is this distortion inequality. And if you put that k equals 1, then you have the Hadamard inequality on the other side, which says that the distortion, that the operator norm of the derivative to power n equals the determinant, which means that you have a conformal map. So k1 means that you have a conformal map. And now kind of if k is larger than 1, what you have is that the differential takes balls to ellipsoid with controlled semi-axis, which is exactly what kind of Rham was telling about in the quasi-symmetric case. But this happens on the level of the derivative. And now you can see that, okay, that the maps that I had before, so that if you have this type of mapping which biellipses in these squares or cubes or something, you notice that these type of conditions are easy to check. Okay. So, but let me now go back to the two-dimensional case, which I kind of, where I said that, okay, in the conformal case, you can use uniformization, you go to the ball and you do this type of thing. So that, and I said that, okay, loosely, I said that it doesn't matter if you introduce a little bit of distortion. So what was the idea? The idea is that if you look these quasi-regular maps where you allow a little bit of distortion, so you still get the same result because there is a classical Stoilov factorization theorem, which is also kind of a version of a measurable Riemann mapping theorem, saying that a quasi-regular map from the plane to a surface with a Riemann nanometric factorizes. Okay, so let's say put a complex structure so that it factorizes through a holomorphic and a holomorphic map and a homeomorphism. So and if you have the homeomorphism under, it doesn't matter. Then it doesn't change the targets. So the holomorphism the holomorphic property then controls everything. But this is somehow this is very two-dimensional thing. You can also do the same thing with a much softer argument by doing it in such a way that you still play the lifting game, but you forget, you put one hand back on your back and you say that, okay, I'm not going to use the uniformization. I don't know that it's a ball. So, but what I can do is that I can look the universal cover. I can look the kind of the original surface I have. I can look the fundamental group. I can look how the growth of the fundamental group corresponds to volume growth of the cover. And I can look the isoperimetric inequality there. And all of these data, I can conclude kind of facts about conformal capacity, which is the same what Rham was telling about modulus of curve families. So that the modulus of curve families going to infinity has positive conformal modulus, and this is different thing what happens in the plane, and that kills the map. If the fundamental group is too large, which means that the fundamental group actually can grow only polynomially, and in the case of in the two-dimensional case, then the topological classification of surfaces gives you the answer. So there are these type of variations for the methods what you can do. The reason why I wanted to mention this is that, as I said, so this two-dimensional thing where you use measurable Riemann mapping theorems and a method like that, they are tied to two-dimensional theory in the sense that you don't really have a good, you don't really have a kind of way to really, you have no existence theory for solutions of Beltrami equations in kind of higher dimensional quasi-conformal geometry, which means that the tools that what you really love in 2 dimensions, they are not at your disposal, but typically you have to use something weaker. But when you have this weaker thing carries over to actually to higher dimensions pretty easily. So Jorma's theorem from 1988 is a kind of a version of this classical complex analysis result. It says that, again, you allow a mapping with a little bit of distortion. Now you are mapping R3 into a closed manifold, and you ask what are the possible targets. So what are the methods? The methods are that you start to study the fundamental group of the target. You use this machine that you lift the universal cover, you look the growth of the universal cover, you use these capacities, blah, 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 blah. And then you conclude that the group actually has more growth. And then you use Thurston's geometrization conjecture or Perelman's theorem to kill all the other possibilities. So there's a real sledgehammer in here. Okay, in some sense, we also use a sledgehammer in 2 dimensions because we use to do differentiation. It is just much more classical than doing it in kind of 3 dimensions. But the Jorma's theorem was kind of so that this was done before the Perelman's theorem, so that it was assuming the answer of the geometrization conjecture, and then you had the answer that if you have this mapping which takes R3, the entire R3, and starts to wrap it on top of the closed 3 manifold, without doing much distortion, then the only possibilities are S3, the product of S2 and S1, and then the three torus and their finite quotients. So you get this type of result. Okay, I tried to do here the 3-dimensional pictures, what I had there. I think I failed. This is supposed to be the same map what we have there, but with cubes. What I wanted to emphasize here is that actually, when you want to go to S2 cross S1, you can actually use that 2-dimensional map, and then you can take away the product of the universal of the covering from R to S1, and this product is possible because you have a bilipsis maps in both coordinates, and then the point to the torus is a product of these classical universal covers. Okay, so that was kind of the status in the late 80s. And so then comes the question that, okay, what about when you go to higher dimensions? So what you can say, okay, so now we know dimension 2, we know the dimension 3, but what happens when you go from dimension 4 onwards? What is kind of the change? It's kind of the change in the topological setting, because these polynomial growth results about the fundamental groups, they don't change. They are dimension independent. You actually have the kind of the sharp result is actually theorem of Baropoulos from the early 90s, saying that if you have a quasi-regular map from Rn into a closed manifold, then the closed manifold has fundamental group whose polynomial growth is at most the dimension of the space, which kind of somehow indicates that torus is somehow the maximal object here. Okay, but the problem when you go to higher dimensions, actually, so starting from dimension 4, you start to see spaces which are not described by their fundamental group. So that you, for example, you take S2 cross S2. Fundamental group is trivial. So, okay. So none of these type of results say anything about that. Okay, we know that in case of S2 cross S2, you just take that map and you take a product with itself, and that's the answer. You know that there is a map to S2 cross S2. Okay, but take S2 cross S2 and make a connected sum with itself, and you don't know anymore. And that's a simply connected space. You don't have the polynomial growth data. The universal cover is a space itself, so that you have to have some different type of way to kind of measure that whether the target is too complicated for the map. And okay, what I find amusing, given that I started my graduate studies early 2000, so that the Ormakas theorem is 88. He proves that you have a polynomial growth. That is enough. Then the Varopoulos proves that you have a sharp bound for the growth of the fundamental group. And these are in the kind of in the 90s. But it was conjectured in 81 by Gromov that okay, not conjectured, but he already asked 81 that what happens when you don't have the fundamental group information. So actually, the date there, kind of the 81 is, I think that's a publication. That this is the hyperbolic groups paper. This is some conference proceedings from 78 or something like that. And so that you can actually find a slightly different formulation of the question, I think with the kind of with the some negative somewhere, but you can ask it in a positive way, asking that are all closed triply connected Riemannian manifolds quasi-regularly elliptic if you just allow some enough distortion, some finite bounded amount of distortion. So that's but if you're now looking at that question, then somehow you are immediately, you start to think that, okay, so what are the quantities that I want to use to perhaps kill some maps? Either I'm very positive and I try to construct all the maps, but then you use after doing that, trying to do that for even for simple manifolds for a little while, you are devastated and you don't want to even look those maps anymore. So you want to have some invariants which kill the maps. And of course, kind of if the fundamental group is out of question, then you want to go to something like homology or something which describes the manifold. And now I put there that we have some early results. Early in kind of I put them. I put a little quotation marks because so Gromov question was from 81, and somehow the first effective result towards this direction was 20 years later by Bonk and Heinonen. So the result of Bonk and Heinonen is that so if you allow some amount of distortion, so that you allow that your mapping can a little bit massage the Rn when it wraps it on the over the target, then what you get is that the target cannot be arbitrarily bad, but the dimension of the Rham cohomology depends on the dimension and the amount of distortion you use. Okay. Okay. I feel that I should say something about the Rham cohomology. And I made a kind of perhaps a little bit unsatisfactory choice to say just the definition. Okay. So what you can is perhaps kind of if you are not familiar with this, but you are familiar with algebraic topology otherwise, so that when you are taking kind of the first courses in algebraic topology, typically you have the fundamental group and then you have the singular homology. And then for the singular homology, you kind of you have the dual theory, which is the singular cohomology. And then if you take the singular cohomology with the real coefficients, then you, in the manifold case, you get the Rham cohomology. So that's the kind of the ways that what you are looking. But the nice thing in the Rham cohomology is that so that you define it using differential forms, and you are having the exterior derivative of the form. So what you are looking is that you are looking forms which die under exterior derivative, and then you identify the forms which differ by an image of something which comes lower. So that it is kind of surprising that this type of analytic type object actually calculates the same thing than the singular real cohomology, but it does. So that what you are doing is that you are looking k-dimensional holes. So that the statement says that if you are looking k-dimensional holes in your space in this sense, then the number of those holes is bounded by a constant which may depend on the distortion. Okay, that's a great result. And actually, many of things that I'm going to talk about today. Little k is so that's the degree of the form. So that you have 1 forms, 2 forms, 3 forms, and so on. Okay, so that it's quantified from 0 onwards, but they all die after n. So that these are non-trivial only from 0 to n. So that when k is between 0 to n. Yeah, thanks. Yeah. Okay, so that's a very nice result. But there's a little caveat, so that if you think, so that then the other result I listed here is a construction of Rham from 2006, which says that this connected sum example that I mentioned actually exists. So the kind of the strange thing related to this question was that it took quite some time to find even some invariant which measures the complexity of the manifold in this sense, but also that it's extremely difficult to construct these mappings. So that the mappings that I have shown this far are pretty much the only mappings people knew until 2005. so that it's very difficult to actually wrap your Euclidean space on top of a kind of closed manifold without breaking the distortion. Okay. Okay, yeah, the parentheses are, yeah, they are here. So S2 cross S2 connects to some S2 cross S2. Yeah, thanks. Okay. But what I would like to kind of mention at this point is that so that when in this kind of Pankka and Heinonen, when they in the paper they proved that bound, so they also discuss what happens in lower dimensions, and they mention in the introduction that what happens in 2 dimensions, what happens in 3 dimensions, and in low dimensions the torus is the maximal object what you can have, and so that they ask this question that are tori cohomologically maximal, meaning that if you have a quasiregular map, is it really that this amount of cohomology you can have, is it always bounded just by torus, and where the bound comes from the dimension and there is no distortion at all? So that they ask this question that they kind of in some precise way, they ask this question that does the distortion matter in this case or not? Because in 2 dimensions it didn't matter, in 3 dimensions it didn't matter, and if you look at fundamental group it doesn't matter, but so does it matter here? And this is kind of the status in the early 2000s in this problem. Okay, so and actually after that there was some time that nothing really happened. So the first result I would like to now really talk a little bit more about is the actually result of Kangasniemi. So in the previous question we ask, we take a Euclidean space and we start to wrap it around a closed manifold. So and then we ask how complicated manifolds we can get. So the dynamical version of that question is that you are looking at self-mappings of the manifold. Okay, so now comes the question that what is the class of self-mappings you should study? Okay, the mapping should be quasi-regular, meaning that the distortion is bounded. But if you iterate, it doesn't really, if you start to iterate, then the distortion bound starts to kind of grow to infinity if you don't have anything special going on. So that the class of mappings you can actually look at, kind of that you kind of then turn to is a class of uniformly quasi-regular mappings. So these are mappings where the distortion constant, the distortion of the mapping doesn't change under iteration. And okay, I didn't write much more about this, but I would like to say a couple of things. Just first for the mappings, because now you start to think, okay, so you have let's say that you have a sphere, and you are looking at a mapping which is, let's say you have S3 or S4 or something like that. You have a mapping which maps the sphere to itself, and you are not allowed to change the distortion along the way. You should be having it somehow very regular. So what are your options? Okay, am I just rotating? So can I really have interesting dynamics in this type of setting? Is this condition too strong? And I think this is actually a valid question, because if you are looking kind of higher dimensional conformal theory, so okay, 2-dimensional conformal theory is very special. You have lots of mappings. You have the Riemann mapping theorem. You have the measurable Riemann mapping theorem. You can construct all kinds of things from data. But when you go to higher dimensions, you go to higher real dimensions. You are looking at conformal map without distortion. then by classical Liouville's theorem from the 19th century says that this mapping is a Möbius transformation. So everything is very rigid. So then you can start to think that, okay, I am trying to pitch you this class of mappings that, okay, distortion doesn't grow. And you start to wonder that are there actually these type of mappings? And the interesting thing is that this class of mappings were introduced by Ibanez and Martin in the mid-90s. And they really, the first thing that what they needed to do is to provide examples. Because nobody the question is that what are the examples? Okay, the easy examples are actually lattice type maps, what you have in the holomorphic theory, in the one variable complex analysis. But then actually what they did is that they developed this method of conformal trap. So the idea is that they wrote down maps which have the property that when you iterate them and you start to follow an orbit of a point, then the point follow the orbit is the mapping is conformal near the point up to one step where you do a bi-Lipschitz change and then you continue with the conformal orbit. Or perhaps the mapping enters this type of bi-Lipschitz region twice or something like that. But that means that if you pick up distortion only once or twice or some finite number of times and you are conformal otherwise, then the distortion constant stays bounded. So that's the conformal. So that this type of conformal trap constructions were first done by Ibanez and Martin in the case of the sphere, and then there are later constructions on lens spaces and other spaces which are spherical spaces. Okay, and but there are actually very few constructions about truly uniformly quasi-regular maps. There are in higher dimensions you can have interesting maps where, for example, the Julia set is a wild contour set, and you can do these type of things, but let me not go there today. The other reason why these mappings are interesting is that there is if you are looking quasi-conformal groups that were mentioned earlier, you have the Sullivan-Tukia construction for an invariant conformal structure. So you have a measurable conformal structure which uniformizes the quasi-conformal group into a conformal group with respect to this new geometry. The Ibanez and Martin showed that the same happens here. So that these mappings, when you have this condition, they carry their own geometry in sense of Riemannian metric, and that the mappings act conformally with respect to this measurable Riemannian metric. So in some sense, what you do is that you don't have the classical Liouville setting where everything has to be a little bit smooth, but you say that your geometry is measurable, and then the mappings don't need to be locally injective. They can branch, and you have phenomena what you have like in the holomorphic dynamics of one variable. Okay, so but having that, so Kangasniemi proved the dynamical version of the Bonk-Heinonen question. So, and you can, the short version is that if you are looking the k-dimensional cohomology, then its size is bounded by the exterior power of Rn, and you get that the size is n choose k. So let me say a couple of words. So what are the ingredients? Because they are very familiar to those who do holomorphic dynamics. So what you have is that you start with this invariant conformal structure that will give you an invariant n-Laplace operator that will give you n-harmonic forms in that geometry. You can look energy minimization. You can show that you have an invariant natural invariant measure coming from pulling back the volume form, and what Kangasniemi proves that this invariant measure is smooth with respect to the original Lebesgue measure. And that is the key, because then what you can do is that he shows that the measure is smooth. He shows that it is represented by the invariant differential forms, and then he can localize the problem to a point. He evaluates in a good point all the forms that he can see coming from the cohomology, and that gives the bound. So these only I know I'm waving my hands widely here so that I almost fly, but the point is that I think that's a very beautiful way to do it. Okay. So, but then of course the question is that, okay, this is the dynamical version. And so so the years actually, these years here are such that these are the publication dates of the papers. Kangasniemi's paper was done 2017 originally. Prives was 18, and they appeared in different order. So what Eden Prives did, he proved the Bonk-Heinonen conjecture, or the answer to Bonk-Heinonen question. So instead of using dynamics, so this would be just n, not natural. Okay, so if you have a quasi-regular map from Rn into a closed manifold, then the de Rham cohomology is smaller than the exterior power of Rn. So here, kind of the question is that because there was the Kangasniemi's proof is kind of dynamics heavy. You really need the dynamical objects to do that. But what Eden Prives noticed that actually inside Kangasniemi's proof there's a compactness argument which you can actually obtain by a different type of localization. I will actually come back to that later, so I don't say it or try to talk about that too much now. But there is a kind of, so that what you can do is that in order to get that again this bound, so that you again you populate your cohomology with suitable forms, you pull them back, and then after a compactness argument, you evaluate the objects you get at the point, and then the forms are linearly independent, and that's why you get the dimension bound. So that's the kind of the idea. Okay, but this actually solves the Gromov's original question, because when you have the cohomology bound this strict, it means that you can now write down your favorite manifold with large cohomology. And for me, this was that you take the S2 cross S2, you add another copy by connected sum, then you take another one, and then you take another one, and then the bound is violated, so there is no map. So no matter how much distortion you want to use, you cannot map into this space. Okay. But this question, so now you start to wonder, because in dimensions 2 and 3, you had a precise list of manifolds which you could reach. And actually you can write down the maps even to those manifolds. So now you start to ask, okay, we know that not everybody can be a target, but can we perhaps actually narrow down which manifolds can be the targets? The problem here, as I was saying, that it's very difficult to actually construct the mappings. So you would like to kind of narrow down the list to as small list as possible, so that you don't have to do anything by hand. That's the kind of the key. Okay, but then when you are thinking, so what happens is that this is saying, these type of results are saying that if the manifold is too complicated, then or kind of too large in this sense, then you cannot map. But how about if the manifold is small? Let's say that you take 3 copies of S2 cross S2. There's no example, and it's not excluded by this type of results. So what happens when the manifolds are small? This is kind of the next question. So again, we turn to dynamics. So this paper is from 2020. So actually, in the dynamical setting, if you have this uniformly quasi-regular map, it is not only that you have the dimension bounds for these cohomologies. It is actually that the algebraic structure you have must be compatible with the exterior algebraic structure in Rn. So because the Rham cohomology, so that when you have differential forms, you can take the wedge product of differential forms. And then when you have closed differential forms and you take the wedge product of those, it will be a closed differential form. So what happens is that the exterior product of the differential forms is inherited by the de Rham cohomology, and it is an algebra. So now you have also the exterior product of Rn, and that's an algebra. So what happens is that if you have a uniformly quasi-regular dynamics living on the manifold, then this algebra has to be so small that it fits into the exterior algebra of Rn. When you do it for 2, then kind of we know all the answers, but it's the same still holds. No, but you're right. So that everything's relevant starting from 3 in some sense. But because in 2, what you have is that the only interesting thing is that you have the one forms or kind of the one covector of R2, and then that's a 2-dimensional space, and it says that this can be only 2-dimensional space. The one cohomology of this space can be only at most 2-dimensional, and that there is no kind of algebraic question somehow left anymore in that case. But when n is greater than the dimension is greater than 3 or more, then this start to be relevant question. I want to say a little bit about this too, because so what is the idea here? So how do you come up with something like that? So the idea actually here is that what you can do is that you have the mapping on the manifold, and the mapping on the manifold induces you a mapping in the cohomology. It's a self-mapping in the cohomology. You complexify and you take the eigenspaces, and then you start to look eigenforms in those cohomology classes. And what happens is that Ilmari shows, the Pankka shows, that when you take the invariant conformal structure and you do, I would say, quite a bit of work, you actually show that these kind of k-harmonic forms, which you see in different degrees, they form an algebra. And actually, that's an interesting case because there's a class of Riemannian manifolds which have the property that the harmonic forms form an algebra, meaning that the wedge product of harmonic forms is again a harmonic form. And this is a special case. It doesn't happen in all Riemannian manifolds. These Riemannian manifolds are called geometrically formal manifolds. So what happens is that the Kangasniemi shows here that if you have dynamics of this type, then the manifolds are conformally formal in the sense of the kind of the smooth theory. Okay, but then when you have the algebra structure for those particular forms, then you do the evaluation, and then you get this algebra embedding, and you are back in the game. Again, I must say I am surprised that this can be done. Okay, but now kind of we have been going a little bit back and forth, so I guess we know kind of we can guess. Okay, so the result is saying that if you have a closed oriented connected Riemannian n manifold, and you have a quasi-regular map from Rn into that manifold, then the Rham algebra of the target embeds into the exterior algebra of Rn. The nice thing here is that when you have this algebraic result instead of the dimension result, what you have is that you can actually look. You can, for example, when you take dimension 4 and you look simply connected manifolds, you know by the theory of Donaldson and Friedman that those manifolds are encoded by their intersection form, which means that they are encoded by their 2 cohomology and the cup product there. Which means that if you have this property and you have this cup product information kind of on the left-hand side, it has to match something in the target side, in the exterior product of Rn in this case. But now you know exactly that the positive and negative eigenspaces of the cup product are at most 3-dimensional because of that result, and then you can go through the Donaldson-Friedman list. You have a table, and you just start to fill in what possible manifolds you have. And so in the simply connected case, you have the sphere, you have the connected sum of copies of S2 cross S2 up to kind of 3 copies, and then you have the complex projective space and the same space with a different orientation, and you can take 3 copies each at most. So those are the possible spaces you can reach. But then there is an amazing paper of Piergalini and Zudas, which studies the question that when you have a branch covering map from the 4 torus into a closed manifold, closed simply connected manifold, and those piecewise linear maps, they are actually quasi-regular maps. And if you have a mapping from 4 torus, it's the same thing as having mapping from R4. So you look to Piergalini Zudas, and you realize that all the manifolds you haven't seen in examples before are covered by the existence results of Bergalinian sudets. So this gives the list in 4 dimensions for simply connected manifolds. And this is a so kind of, let me say quickly, so that in some sense I also kind of I didn't really anticipate this type of result when I first read the Bonk-Heinonen paper in something like 2000. But this, I kind of like that there's some appeal. I think there is some geometric appeal in this result, which is that if you take let's say that you take the 2 torus, and you take these two circles generating the fundamental group or the first homology or something, and you think that you look what happens with the typical covering map, what was in my first slide, then what happens is that you have here the crossing point. Let's say that my crossing point is here. If I look this circle, it leads to a circle like this. So if I orient this like this, let's say that it goes this way. And then if I have the other circle going that way, it leads to a line like this. So what happens is that because the mapping is extremely nice mapping, we can see that the intersection of the one-dimensional homology classes, it doesn't lift to a homology class because we are in the plane, all the homology vanishes, but there is still this geometry left which says that that we see the same type of intersection. So what is this somehow saying? I'm very loose now. If you are looking on this your target manifold, you are looking homologically relevant submanifolds which intersect, and you are looking all kind of the intersections you want to look. Then you have to be able, in order to have a map, you have to be able to realize all those intersections simultaneously in the Rn. And in the sense of the exterior algebra. But what is exterior algebra? The spanning elements are oriented K-planes or oriented subspace, kind of subspaces. So what you have is that you have to be able to kind of find enough subspaces which intersect the same way as the manifolds or the submanifolds do in the closed manifold. This is the heuristics for me, and I didn't see this coming. Okay. So but actually, what is kind of interesting that the story doesn't end here. So actually, Fedja Manin, who is here at the University of Toronto, and Eden Prives, they used the cohomology embedding result together with some hard Lie theory, which I definitely don't understand. They proved that the fundamental group of the target manifold is virtually abelian. And I must say, this is an amazing result because, let's say it's an amazing fact because okay, there's the big Gromov theorem saying that if you have a group of polynomial growth, then it's virtually nilpotent. And now what you would like to do is that you would like to kill the nilpotency and prove that the group is abelian. But if you have an embedding like that, you can do it by algebraic methods. So you have that the fundamental group is virtually abelian, but actually that means that you can actually go through all closed form manifolds because you know what are the possible fundamental groups. You pass to a finite cover, and you see that the fundamental group is Z2 or kind of C4, and here you have a Z2, and C4. And then you add those, what you had manifolds in that list, and that are all the possible targets. And these manifolds are kind of well known. The original construction gives mappings to those manifolds. This is very nice. Yeah, the same assumptions. Yeah. Okay, so this is very recent. This is the archive year. Okay, so I have a couple of minutes. Okay, so that sorry. So that if you mean this theorem, So that the assumption is that we have a closed oriented connected Riemannian n manifold which is QR elliptic, meaning that there is a mapping from Rn. That's the only assumption, and then kind of you can use that theorem to get the cohomology embedding, and then you can use that to prove this. Actually, this is actually very interesting. This is so. I wrote kind of 3 lines about the proofs, but let me say this actually instead, because actually, so Fedya has a series of work with Alexander Beretnikov and Larry Goof about Gromov's elliptic manifold. Elliptic manifold is a manifold which assumes a asymptotically positive degree map from Rn, and I'm not going to define that. But they have a kind of, but in that case, what you do is that you work with Lipschitz maps. And actually, they can prove much more in that context. They can prove result like that, and they can prove that actually you have a mapping from a torus. But then that's a Lipschitz map, and it's not a branch cover that what we need in this theory. So there is now the interesting so that now Fedya's work kind of combines now these 2 totally different areas now together, and I find it very interesting. Okay, but let me say a couple of words about the ideas that why on earth anything like this should be even true. So, okay, I'm sorry about the slide, but let me try to draw a picture. So, the key fact in this whole thing is that if you have this kind of entire quasi-regular map, then it really kind of equidistributes over the target manifold. And this is like, I think I'm abusing the terminology, but let me do it like kind of by saying that it equidistributes, but this is really what's gonna happen. So think about that you have on your target manifold, you have 2 functions supported like this. And then you have your mapping. So then what happens is that when you compose the function with the mapping, you start to see the bumps here on the domain side. And actually what happens is because the mapping doesn't distort the geometry, then in large scale, the pre-image for both functions looks essentially the same. And this can be kind of formulated using one function in this way that what you do is that you take the function on the target side, you compose it with the mapping, and you integrate it against the Jacobian. So this is actually so this is the pullback of this form. But then you average it with a general amount what you cover. And what you have is that the ratio tends to the size of the function. So that's the equidistribution. If you play with 2 functions, you can show that the ratio of these type of integrals tends to 1. And it happens for all radii going to infinity except a little possible exceptional set. And those who know or perhaps more familiar to the Nevalna theory than me, they recognize these type of things. But what is this? What we do is that we do the previous thing. Instead of looking at the map, we localize the map into a ball. So what we do is that we take a unit ball and then we scale the unit ball into the space in such a way that we start to capture more and more the Jacobian of the original map, and we have a doubling property what for this type of Jacobian. And then when you have that setting, what you can do is that you have this weak convergence for the pullback, so that if your form is exact, you pull it back, and this type of integrals die. This is the same what happens in the dynamics, and this is where how you construct the invariant measures. This is this type of machinery. Okay, so then you notice that the Rham algebra is an algebra, but if you start to pick forms, they don't form an algebra. But this normalized pullback operator formalizes whatever choices you had. So when you pull back, you pass to the limit, suitable weak limit, you get an algebra out of the forms, whatever form you picked, representing the cohomology. And then so that you have to use kind of some tricks. You don't have enough convergence, so you pass to some Poincare lifts of the operators and blah 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 blah. But the idea is that you use this normalized pullback, and that is kind of associated to the equidistribution. That's really the key. And then you prove that when you start pulling back, you get the limiting operator, which is an algebra homomorphism. And then you notice that if your target is not a sphere, then you can do this also for top dimension, where you only have L1 regularity, and you actually don't look forms anymore, but you pass with the weaker limit of measures and some technical difficulties. But then what you do is that you get an embedding of algebras, and then you again do the same thing what Kangas did in the first place. So you evaluate at a good point, and then you get an embedding of this. Kind of what you have is that you have so this algebra embeds into a subalgebra, finite dimensional subalgebra here, and then you have this evaluation map, which gives you the subalgebra in the Euclidean space. And I think I will spare you for more. Thank you.